Good morning. I am Pradyut Dubey of Chemical Branch, and today I'm going to talk about my ELL100 project. About my project. In this, I'm going to analyze both real and ideal transformation along with the core losses concepts of magnetism used such as Faraday's law, self-inductance, mutual inductance, MMF, etc. And also I'll be analyzing the problems, losses, both core and resistive and heating loss. And also and using these transformers, I'll be analyzing the electrical power transmission circuit using the ABCD parameters of a two-port network, three-phase line, and step-up and step-down transformer. Now, our content is the history of the power transmission and transformers, principles and working, lecture concept, diagram, inspiration, what I learned, and the bibliography. Basically, this is based on the electromagnetic induction. The principle is the principal operation of the transformer, which was discovered independently by Michael Faraday in 1831 and Henry in 1832. So basically, this is just some information about the experiments which Faraday performed and other people performed, which led to the discovery of the modern transformation. So finally, from these experiments, the modern transformation was invented and modern power transmission system was invented. And now we come to the history of power transmission. So the first, actually, the in the power transmission, a DC current was used, and for the first time in 1881, alternating current was used after Lucien Gollard and John Dixon Gibbs built what they call the secondary generator, an early transformer provided with 1:1 turn ratio and an open magnetic circuit. And basically then a little more about the history is given here, and then rapid industrialization in the 20th century made electrical transmission line and grid circuit infrastructure item most industrialized nations. Now we are talking about here an ideal transformer. In an ideal transformer, theoretical linear transformer that it is lossless and perfectly coupled. Perfect coupling implies infinitely high core magnetic permeability and winding inductance at zero magnetomotive force. Both coils receive the same amount of flux. By Faraday's law and power relation, we get this. This is the basic power law, the basic relation for transformers. Also here, the impedance I, the ZL dash is the impedance of the this driving point load, and ZL is the normal load impedance, and A square is this parameter here which we have defined. A real transformer also works on the same principle except that loss due to leakage flux as a result of not proper winding, hysteresis, eddy currents, etc. exist. Now, what we have learned, lecture concepts. In the lectures, we were directly taught about transformers working losses and transmission. Transformers basically used in power transmission to minimize losses due to resistance of wires in long range transmission. Basically, a power transmission system consists of a step up transformer, transmission lines, and a step down transformer. Electricity is maintained mainly transmitted at high voltage over a long range to reduce losses as current will reduce. We are only interested in terminal characteristics of transmission line because we are not interested in what is happening actually in the line, but only what we are giving and what we are receiving, which are the voltage and current sending S and receiving R ends. The transmission line itself is then modeled as a black box, and a 2 by 2 transmission matrix is used to model its behavior as follows. This is your ABCD parameter. The supply here was also used a three-phase supply with phase angle between two supplies given as 120 degrees. We generally reduce the transformer into this equivalent circuit for easier calculation. Here the winding, joule loss and leakage resistor are represented by the following series loop impedances of the model. Here the primary winding is given by RP and XP, and the secondary winding is given by RS and XS. And the core loss of reactance is represented by following shunt leg. RC is the core loss or iron core losses, and the magnetizing reactance is XM. RC and XM are currently termed as magnetizing branch of the model. So basically this is the equivalent circuit of the transformer. Here also we can see that there gaps can exist which can lead to the leakage of flux. Now here, let's talk about the basic power transmission line. We have a power generating station which uses three-phase rotating generator to create the electricity. Here we have a step-up transformer which increases the voltage of the line and decreases the current. Here there is a long-range transmission which and due to small current there is a minimum loss here. Here at the substation we have a step-down transformer which increases the current, and now this current can go to the sub transmission customer, a primary customer or secondary customer. So basically this is the basics of a power transmission line. Now where did I get inspiration to study about this? Just a second. Basically, I have always been interested in power supply lines and by the fact that they can transmit electricity over thousands of kilometers. I have always thought about how engineers set up lines around the country and how costly would be the process, how much energy would be used, and also what is in the transformer in the power stations. Carrying this curiosity, I made an effort to research this area and make this project. What I learned from this project. This project has helped me to come off the theoretical lecture knowledge and explore the practical applications of the transformer, power lines, and electricity transmit. After finishing this, I have developed a better knowledge of this topic. Thank you. This is all for my project, and I hope I made it well.